work in neuroscience and brain-machine interface at Stanford, and I'll be talking about some of the work that we do, specifically in regards to restoring functionality for people with motor paralysis. So I'll take you guys through a typical signal workflow, and you may find that many of the concepts that we talk about are things that we've seen as a part of this class. So as an introduction, I'll show you guys these two videos. And just as a context, like some of these words in this first video might be a little bit confusing, but don't worry, we're gonna kind of use this as an example and step through each part of it. But just kind of make some observations about what's happening, and then maybe think about some of the words this person is using.
Our goal was to build a high-performance BCI that can restore communication to people who are locked in by using handwriting motor imagery. We tested our BCI in one study participant who was implanted with 2 microelectrode arrays in hand area of motor cortex and who was paralyzed from the neck down. Here's how our decoder works. We use multi-unit threshold crossing rates as features. A recurrent neural network decoder converts these into the probability of each character being written at the current time step. The probabilities can be thresholded to emit discrete characters, which we did for real-time use. Offline, we explored using a large vocabulary language model to autocorrect typos. Here's what it looks like in real time when our participant uses the BCI to copy a sentence shown on the screen. Our participant is typing freely and entirely at his own pace. Note that our decoder is fully general in that the user can type any sequence of characters, including sentences that never appeared in the training data. In the next video, we compare our handwriting BCI, shown on the top, to the current state-of-the-art performance for intracortical BCIs, shown on the bottom. In both videos, the user is copying the same sentence. Our handwriting BCI is more than twice as fast as the current state-of-the-art. To our knowledge, the typing rates we achieved set a new record for BCIs of any kind.
Okay, so I think this is a little bit, this is not as relevant. So what are you guys' reactions? Maybe I can get a chat, some responses in the chat. What do you think we just saw just now in this video?
So the AI, well, first it measures brain waves, and it seems to be able to make sure that they're above a certain threshold, i.e. someone think, you know, I might want to do this, won't figure it, because that'd be kind of unfortunate. But it also has like a bunch of different steps. It's not just like, okay, we just looked at what they're probably trying to write and then we vote that. No, it also has like typo correction and stuff.
Yeah, exactly. So it's a pretty sophisticated algorithm, but I guess what I wanted you to take away is that person thinks to handwrite a particular letter, and then through some sophisticated decoding algorithm, we decode the letter that they're imagining the handwriting. Obviously, they can't actually do the handwriting because they're locked in. I don't know why it's not going full screen.
Our goal was to build a high-performance BCI that can.
But yeah, so yeah, okay. So I also wanted to show you this one briefly.
In this paper, 2 people with tetraplegia, that is 2 people who were unable to move their arms or their legs in any functionally useful way, were able to control a prosthetic or a robotic arm simply by thinking about the movement of their own paralyzed hand. And they did that using the investigational BrainGate neural interface system.
So here, very similarly, we use once again the brain data taken from these recordings, and we use it to control a robot arm. So here, the overall theme that we're trying to address is that people who are paralyzed can't move their limbs, and thus we record from the brain and use the information that we get from the brain recording to interface with the outside world in some way, because these people have lost that functionality. So what about this looks familiar? So I guess it's a pretty complex figure, but one thing I thought might be kind of a little bit more familiar is these probabilities. So we've seen probabilities like this, maybe also this NN, this neural network. We haven't looked at this particular type of recurrent neural network before, but it is a neural network. Ultimately, we've seen that before. And then also we're making probabilities for a bunch of different characters. Okay, So cool. So let's step through each of these one by one. Okay, so I'm going to face this as a computational problem. Based on that, what do you guys think are the inputs and outputs to my problem? Yeah, okay, great. Thanks, Arav. We have input is the brain waves, in this case, electrical signals to the brain, and outputs are letters to write. So that was in the first one. So for example, the first one where we classify the type of letter, and then in the second one where we maybe classify which direction they want to move. So maybe there we're doing a problem where we kind of map the velocity of the arm, or the velocity of the direction of the way they want to move. So to understand about this, we need to kind of think about a little bit about the brain. So the brain is very complex, and it's also very relatively compartmentalized. So we've looked at so in the neural network, we looked at some kind of vision, and the vision portion of the brain. So we said that, hey, in a convolutional neural network, the early layers recognize edges, and then they recognize more complex features, and so on and so on. Similarly, each part of the brain does a slightly different thing. So here you can see the front part of the brain has kind of these more intangible things like emotions and inhibition. Here we have a motor portion of the brain, which we'll be talking about today, voluntary movement, sensation, and things like that. So there's each part of the brain does a little bit different, has a different function. So depending on where we're recording, we can get some of these different functionalities. Okay, I also need to tell you a little about what neurons do. We've kind of already looked at this, just as a quick reminder. Here's a neuron. This is a cell, and then it has many connections to many different neurons, and then it also connects as inputs and outputs, as we've seen, and then they spike. So this is the basic unit of communication of a neuron. So if you stick an electrode right up here, right close to this, and you measure the voltage across right here, you're going to get this kind of voltage versus time pattern. So a quick up and then a quick down, and it's called an action potential or a spike. So how do we record from the brain? So the basic idea is that we stick these metal electrodes into the brain. So as you can see, the scale here is pretty small. So this is something called the Utah array, and each of these little needle-looking things is a electrode, and you can measure the activity from the brain using these. There's also some different newly created. Yeah, you have a question?
So does putting that in your brain hurt?
So the brain,
it looks like it would hurt like a lot.
Yeah, that's a good reaction. But if you think about it, we've evolved to protect the brain, and pain is a evolutionary response to like protecting from danger, right? So because the brain is inside the skull and it's highly protected, there are no nerve endings in the brain, so it doesn't hurt per se. Yeah, so as someone said, there's no pain sensors, so it's not going to hurt. Maybe when you do the implantation itself, you have to remove parts of the skull, you have to do that surgery, so maybe that part hurts. But yes, I think you've touched on a very important part, is that it's an invasive thing to use these things. So that's a big barrier to implementing them. And this is a different kind of array in which instead of lateral position, you go deeper into the brain. So it's along this little shank that you can see here. And here's an example recording you might get from one of these probes. So here we're looking at 384 channels of voltage recording. And the goal here is to kind of look at which of these are spikes. So which of these patterns correspond to a neuron spiking. So you can see here kind of this action potential looking pattern. Here is some noise. So you have to kind of, the problem that we're trying to solve is, one of the problems is trying to get the spikes from this noisy looking mesh of data. Okay, so this is a problem that I think we've all seen before. So how do we translate these voltage signals into something a computer can use? And it's not exactly obvious why, but if we look at the times at the spikes, and then we simply say, if a neuron is spiking here, we're just going to say a 1 in that particular time bin, and then a 0 elsewhere, this is a very good way to get to recollect information that the neuron is communicating. So if we use a vector containing spike times, we now have a numerical vector representation of what this neuron is doing. So it turns out this works very well for decoding. Okay, so in terms of the big picture, I just wanted to give a quick recap. So here we have the brain, cortex. The brain is doing some kind of computation, so we're getting some visual feedback from here. We're implanting an electrode array into cortex, and we're recording the neural signals. So far, I've said that we've detected the spikes using some signal processing methods, and then simply saying when does the spike go above or below this. And now we want to use a decode algorithm, and we want to decide this. Okay, so there are many different types of decoder algorithms. So here, maybe let's say we're looking at the type of letter. So what type of task is predicting what letter someone wants to select? Thanks, Drew. How about, yeah, classification, right? Great. So, and then as we talked about what algorithms you might know, might work for this. I'll show you this in 1 second. And then how about for a keyboard type continuous task? I kind of gave this away. What type of task is that? Okay, Drew.
What does that mean exactly?
So we've talked about 2 different types of tasks in our class, right? One of them is classification. And then so when in classification, we input some data and then we output, so in this case, 1 of 26 possibilities. So what kind of thing I want to decode to this classification? Yes, so I have some regression options, exactly. So for a keyboard type continuous task, we might be trying to predict which direction we're going.
We present a sentence, we present many sentences.
So
when the sunlight strikes,
I want to try to make this model,
raindrops in the
first
air.
trying to use this cursor to think about how you might
see her typing back,
code this.
And this gives me the opportunity to also point out one other very important
up with the velocity of blank or left with the velocity of blank. So if I'm trying to decode that, it's a continuous variable. So you might imagine that you do a regression type task. Okay, so now let's say I tell you that my data in this 2-dimensional space looks like this. Okay, so a keyboard type continuous task. I have a question on what that means. It's what I'm showing.
We present a sentence. We present many sentences. When the sunlight strikes, raindrops in the air.
A participant who's logged in is connected to this computer, and they use this.
And you can see her typing back. And this gives me the opportunity to also point out one other very important point. And this is the axis with engineering that Brian was pointing at. This is not a normal keyboard, as you note. This is an optimized keyboard, right? Our human-computer interface colleagues across the street in computer science would slap us if we didn't do this. Of course, we've clustered in the center.
Does that make sense? Okay, cool. Yeah, feel free to ask questions. You can also unmute, no worries. Okay, yeah, the talking in this isn't really important, but we can. Okay, so I think that there's been some comments that we'd like to audio video.
We present a sentence. We present many sentences. When the sunlight strikes, raindrops in the air, and you can see her typing back. And this gives me the opportunity to also point out one other very important point, and this is the axis with engineering that Brian was pointing at. This is not a normal keyboard, as you note. This is an optimized keyboard, right? Our human-computer interface colleagues across the street in computer science would slap us if we didn't do this. Of course, we've clustered in the center the letters that are more frequently selected and put Z and X out on the periphery. Why wouldn't you do that, right? A QWERTY keyboard is ridiculous. It dates back to when you had little mechanical.
Okay, so that's I guess that was the audio. If it makes sense, then he's talking about how because you don't have the reason we have keyboards in the layout that they do now is because we're used to it and we are accustomed to it, and therefore we'll continue to use them. But if you're creating a keyboard layout from scratch, you would imagine that you put all the most accessed letters, excuse me, most accessed letters closest to the middle or where you spend the most time, where it's easily accessible. Okay, does that make sense now? Cool, great. Okay, so let's say, as I said, I show you this neural data in 2D space, and each of these are labeled clusters. Can anyone tell me what kind of algorithm they might use? Does this remind you guys of any algorithm that we've seen? Yeah, k-nearest neighbors, right? So definitely for this one, it looks pretty. The data looks pretty. And there looks like there's good clustering. And as I said, if you make an error, for example, this N and H, you can also use context dependence in the model afterwards to say, hey, this looks like D, so you can kind of autocorrect it that way. Okay, so now we've kind of summarized our computational problem. So input are neural signals and spike times, and output is the tracking of movement or classification, depending on what kind of structure you want your brain-machine interface to do. Okay, so I'm just wrapping up future work. So as we've pointed out from the very beginning, this is an extremely invasive implant. You have to, so if you're going to use this, chances are that you're in desperate need. So this is not going to be used for someone who's well and able, most likely. How is it going to be commercialized? You might have seen this guy. This guy is Elon Musk. He has a company who's relatively recent doing Neuralink. And there's a really good video a few years back about monkey mind pong. I'll just show you a minute or so of it. And then we can improve decoder algorithms, leveraging computational improvement, so you can increase the complexity of the model. These days we use very sophisticated neural networks. And then also you can, this is not only confined to motor. As I said, the brain has many different areas, and if you record from those different areas, you could presumably use them for different functions. So I'll just show this very briefly video.
Targets. One of the things the Neuralinks allow Pager to do is to play his favorite video game, Pong. To control his paddle on the right side of the screen, Pager simply thinks about moving his hand up or down. We've removed the joystick altogether. Now that he's up to speed, let's increase the difficulty and see how well Pager can play with the Neuralink.
Yeah, okay, so I think this is the same idea where we try to move. You think of moving your arm, and you get that feedback on the cursor on the screen. Okay, any questions?
Mr. Targets.
Yeah, Drew, question.
So theoretically, could you hook up any action to any specific thought in the brain? Like, for example, if you wanted to, for some reason, have the thought of your computer turning on, make your computer turn off, which would be annoying. Could you do that, even though they're the exact opposites?
If I'm understanding your question correctly, the question is, what is the mapping of one particular decode to like some kind of external interface? Is that the question?
I'm more asking, is it possible to map a certain thought to an action that is not related to that thought?
Yeah, I mean, in this, I think it's extremely unlikely that you would encode, that you would like create a system in which, like, so for example, in order for like you thinking up or something to turn off your computer, you would have to like explicitly code that into your system. So as long as you use motor actions to measure consistent action potential patterns. Yeah, definitely. Yes. Okay. So in that case, you would have to like explicitly code it to turn off the computer and stuff. So I don't think that's extremely likely. But depending on how good your decoder algorithm is, you should probably keep that confined to the particular application. It's like saying that, oh, in a video game, if I click X, I could quit the thing. So while you're inside that game or the application, it's not going to happen. Okay. So I think I asked the question. There's definitely a part that I glossed over. So is how does the spikes? So we looked at spikes, right? So we looked at these spike times. how does that control, how does that relate to moving the ball to a certain place? So that is a little bit confusing, but I mean, we have looked at other confusing examples in class before, right? So how does demographic relate to, like, for example, in the criminal justice project, how does demographic relate to, like, let's say I'm predicting X, Y from X. Sometimes these X and Y variables are very not related, but the decoder, because it's complex, can figure it out. So like in the convolutional neural network, the inputs are just pixel values. How can that be so related to something so complex as if the image is a cat? So the decoder can recover structure in something that's so somewhat very seems unrelated. So I would say that that's one way you could convince yourself. The other way is that there's a little bit more sophistication going on here. Neurons are kind of like tuned to certain directions. So this neuron is only going to fire high if the participant is moving their arm right. So that, if I tell you that, then maybe that's a little bit more convincing. Yes, a lot of data. So 384 channels times, or maybe 1 or 2 neurons. So it is a lot of neurons, but no, not as many neurons as you might think. So about 500 neurons firing at 30 kilohertz sampling. So you're taking a ton of data, definitely.